Hello, my name is Hamid Jamshid. In today's session, I'm trying to continue my last discussion on the free body diagrams of different objects to be able to solve the static equilibrium equations. At the beginning, I would like to start with the definition of a two-force member. Actually, in many static equilibrium questions, you may face with a two-force member. What is a two-force member? Is a member which is massless, or the mass is negligible, and only two forces are applied on the end points. If you have such a condition, the forces have to be exactly in one direction and on the line which is connected to point. Let's assume that FA is applied on point A and FB is applied on point B. They cannot be what they want. They cannot be an arbitrary direction and arbitrary value. They should be exactly the same value in opposite direction, and they are aligned with each other, and they are crossing through both points of A and B. It is possible to prove this condition, and the proof is not hard proof, but let's keep in your mind that whenever you're facing with such a condition, you know that there is only one unknown. You know the direction of the force, and the only thing that you don't know is the magnitude of the force. As example, here I have a hand which is applying some forces on this arm, and this guy is connected to that one. One of the things that you should be careful about is the shape of the two force members. It could be any shapes. For example, here it could be like a rectangle, or here it could be like a part of a circle or whatever. Regardless of the shape, as soon as you know that you have 2 point of conditions and there is no external forces applied on this and the mass is negligible, you can put the forces like this. And if you want to see how many unknowns do we have on the arm ABC, at A I don't know AX and AP. It could be presented at the magnitude of the force at A and the angle. These two are unknowns. You can say it's AX, AY, or you can say that FA as the magnitude and the theta are unknown. The number is the same, two unknowns. And when you go to B, you know the direction of that because you know point D and point B, and based on that you can say, okay, the angle is, for example, in this case 45 degrees, and we are pretty sure that the force is exactly in this direction, but we don't know the magnitude. Then point B is not adding two unknowns, it's just adding one unknown, and that's the magnitude of the force at that point. And in total, if we consider the free body diagram of this part, we would have 1, 2, 3 unknowns, including two magnitude of the forces and one angle. As I said, you can replace these two unknowns with a y and a x as two forces, and there is no difference between having theta and the magnitude or fx and fy as your unknowns. The number is the same. This is it for two force members, and you may have many of them in your exams, in your assignments, and you need to be careful about them, because sometimes if we generally consider this, we may add two unknowns here and say, because this is a hinge and this is a hinge as well, I put two unknowns here, two unknowns here, and two unknowns here. If you do that, you cannot solve this, because you would get 4 unknowns in total for this part, and you have only 3 equations, and by having 3 equations you cannot get to by having 3 equations you cannot get to 4 unknowns, and you should be careful about these parts. There is one hidden information here, and that's the angle of the force, which is like this. Okay, let's go to the next page. Here I have some examples. I want to go through some of these examples or all of them and try to find the free body diagram of the beams, and using the information which was provided in the last session. In the last session we said we need to put the forces based on the joints that we have. For example, the hinge does not let me go up and go to the left and right, and that's why I would put two forces, but hinge let me to rotate it. Let's forget about the rest of the mechanism. We just consider a small part of this, and you would say hinge generally lets the beam to rotate, and that's why it cannot provide any moment, and that's why you just put one force here, a y, and one force here, a x. And this is one of the position that I'm going to do. I'm just getting rid of the hinge to do the free body diagram of this AB beam. The other thing that we need to get rid of is the cable. We just remove a cable and replace exactly a force which is exactly in the direction of the cable. Let's name it B. And right now you're pretty sure about the direction of this, meaning that you have one unknown here, which is the magnitude of the force B. You have two unknowns here. One of them is the magnitude of AX, the other one magnitude of AY. And as you know, in the planar cases we have three equations and three unknowns, and we can solve this. Okay, let's get to the next one. In the next one we have point A here and point B. What we have in point B is a roller, and what you need to consider for the rollers is that how they can point the beam at point B move. If you consider this, as I said, forget about the rest of the mechanism, just consider portion, a small piece of the beam, and let's try to move it. As you can see, you can do motion parallel to the slope, and you cannot do motion in this direction, meaning going through the slope, but you can slide on that, meaning that this connection or this joint cannot prevent the motion in this direction, cannot provide any forces in this direction, but it can provide some force in this direction. That's why I put a single force like this here. A, like before, would be a y and a x, would be a y and a x, and meaning that here I have two unknowns, and the other unknown is the magnitude of this, and the other force which is applied is an external force, which would be exactly at the known point. We don't care about that, it's applied on the system, and we need to consider that in sigma of x, sigma of y, and sigma m. But the point is here how to replace this, and we have just one unknown, which is the magnitude of force B. The same story here, with the difference here we have a force which is applied in a known point. Here we have a moment which is applied on the whole structure, and for example here you need to consider sigma of x. This point would be in sigma f, this force would be in sigma of x, sigma of y, and sigma m. But here you don't have any external forces, you have just one moment, and this would be in sigma m, and it does not show up in sigma of x and sigma of y. The same reasoning for this, you would have one a y and one a x at point A, and if you consider B is not letting us to go toward the left or right, and that's why I put one single force over there. The other kind of joint that we may have is like this. They may name it slider or collar or something like that. The way that this joint works is like this. It lets this slider go up and down, but does not let go to the left and right, and it does not let the rotation, meaning that if you start to rotate this piece, you start to break the whole joint, and meaning that this apply two reactions for you. One of them is the forces, which is horizontal forces, and the other one is an M. Name it MA and name this guy AX, but we are pretty sure you cannot provide any AY. And in this point B, similar to previous cases, you have one single force which would be in the vertical direction. Name it B. And as you can see, we have only three unknowns here, and we are able to solve this problem. Okay, let's get to the next one. The next one is similar to the previous ones. Just put some forces at point B here, because it's hinge By and Bx would be what we have at point B, and point A we have just one single force, which is a vertical force Ay, only three unknowns. And if we go to the other one, which is case F here, at point B we would have just one force, and here we would have Cx and Cy, meaning that it does not depend on the direction of the joint. In all of these cases, the direction of the hinge is vertical, but you may have the horizontal one. Does not make any difference, and you would have two unknowns over there, and still you can solve the problem. Here you have Cx, Cy and By, and you are able to solve this problem. Okay, some more examples here. Let's go through this one and see what we need to do. Here we have a hinge which is known, and we know that the hinge has two reaction forces. Here we have a roller or something like a wheel, and you need to consider this carefully. The point is that you need to see how you can move. You can move in this direction, but you cannot move in this direction, and that's why we need to put a force in this direction perpendicular to the surface. And at A it's clear, Ax and Y, and no problem there. And in many cases you get the angle of the slope, and what you're looking for is the exact angle of the vector that you're putting there. I want to show you how to find the angles if you're doing this. If you consider this one, it would be perpendicular. The force of P would be perpendicular to the surface that the roller or the wheel is rolling on. And in this case, if you add a vertical line, you can say this angle is 30, this should be 60, this is 90, then this guy should be 30 as well, because this is 180 in total, this is 180, I got this 60, I know this is 90 because of this, and this should be 30 as well. Then you can have this in your mind that in these cases this should be 30 degrees, and then you can find the sine and cosine of that, the projection on the x and y axis, and make it easier for you to solve it. As you can see, here we have the solution ax and ay, and a force with 30 degrees angle with the vertical. If you consider this line, this line also can be considered, and this angle and this angle are equal. This is 30, this should be 30, and this is 30 as well. Okay, another case is here when we have a roller, when we have a roller here, and when we have a slider here, and a point which is where we are applying a single force and a single moment. We are applying both of them. As I discussed about this in the previous page, you know that this kind of joint lets us to move in y direction, and that's why we don't have any ay here. And it doesn't let us to do motion in this direction. That's why we have ax, and doesn't let us to rotate, and that's why we have ma. And in point B it's clear because we have motion. We can have motion in this direction, and but not in the vertical direction, and that's why we have nb, which is a normal force at B. And for considering the motion that I'm mentioning a lot, you just need to consider a portion. Don't consider the whole structure. It would be completely confusing. But if you cut this and just try to move the single piece, a small piece of this, you can do motion in vertical. You cannot do motion in horizontal direction, and you cannot rotate it, and that's why you got these two values over there. And the same story here. Don't consider the whole mechanism, just a small piece of that, and try to do motion. You know, if I have a small piece here, meaning that I have a roller, a beam connected to that, and let's forget about the rest, you can do rotation. It does not prevent you. That's why we don't have M here. You can do sliding to the left and right. That's why we don't have any forces here. But you cannot go through the ground, the surface that you have here, and that's why you have a force here. This guy is preventing that motion, and that's why we have this here. Okay, as you can see, we would have 1, 2, 3 unknowns, and it is possible to solve this. And let's get to this one. This one is like this. If you consider the point A, you have 2 unknowns here, and you can get only one other unknowns because you are dealing with one piece and you have 3 equations. Accordingly, this guy should be a 2 force member, meaning that it's not adding to the unknowns 2 variables, it's just add a force here. And then if you want to plot the free body diagram of that, that would be a x and another force here, a y. And for DC we have only a single force here, and that would be, for example, DC, and the direction is completely known, and the only thing is the magnitude. Then we have 3 unknowns which could be found based on the set equations that we have. Okay, let's get to the last one, which is here. I have 3 connection points for this, and the thing is that how is that, and what direction should be that? The same idea that we discussed here. We are just considering a small portion of this, not the whole structure. Right now, somebody may say that the force should be like this. The other one may say that the force should be like this, and what should be the correct one? Or here, it should be like this, or it should be vertical, and here, what are those? The key word here, smooth contact, meaning that there is no friction on these surfaces, and these connection points can slide. And if you consider only a single portion, small portion of this, and let's forget about the rest of that, you have a tilted beam which can slide, right? But it cannot go through the surface, and that's why we need to have a force in this direction. And if I want to put a force at point A, I need to put the force like this. This would be my unknown at point A. I know the direction. The same story for B. In B you can do a slide to the left and right, but you cannot go through the wall, and that's why you would have a force like this at B. That would be By. The trickiest one may be C. In C, if you just consider a portion of this, you can do a slide in this direction. It does not prevent you. But you cannot do slide in this direction. You cannot do motion in this direction. That's why what you would have is exactly this, and this is what you get in point C. And you have three unknowns, three equations, and you can solve this problem. And based on this, you know how to develop your free body diagrams for 2D problems and solve the static equilibrium equations. I have some more examples here. Let's go through them, and there are some differences here. Let's go through the first one. The first one here, I have a link named ABC, and it's connected via some cables to the roof. And let's try to see how many unknowns do we have. Let's assume this is for example 5 kilogram, and it's a known value. And if I start to cut everything and get rid of everything, what I get here would be a x and a y. In point B, I would have a tension here and another tension here. And if you want to name them, let's name this point D, and this is B, or we have 1D here. Let's change the name here. Name it E, for example. If you want to name this B and the other one E, we would get 4 unknowns here. But there is a good relation which we know about the pulleys and cables. We know the forces which are applied on the cables which are going through a pulley are equal, meaning that if this guy is B, this should be B as well. If it's not, this pulley starts to rotate, meaning that the moment of this guy is not equal to the moment of this guy. The moment of this guy around this point would be B times R. R is the same for both. The other one is B times R as well. And this is static. We are talking about static equilibrium, and everything here is not moving, and nothing is moving here. Then when you have B here, you should have B here as well, meaning that you don't have any new variable, and this variable is B as well, meaning that you have 3 variables and 3 unknowns here, and you can solve that. Okay, let's get to the next one. The next one is like this. You may face with some joints like this, and you need to figure out what is happening here. The thing is that it's like a roller, it's like a beam, and as you can see, you can go up and down, but you cannot go left and right, and you cannot rotate this, meaning that you don't have any AY, but you have a X here, which is preventing you from going left and right, and you would have M here, which is preventing you from doing the rotation at that point. At point B would be BY only, and 3 unknowns. If we go to the next one, you have a cable. You can get rid of the cable, put a C force here. You have a roller. You can put BY here. This is CX, which is like this. And in point A, there is a hinge here and also a slider here. Let's cut this and consider this only, meaning that if I want to show you like that, you have a slider which is going like this, and that would be a link attached to that. By cutting, I mean forget about the rest of the mechanism. You have a blue part, for example, here, which is connected to a slider, and you want to say me that how does this can move. I would say because we have a hinge here, this can do rotation. That's why we don't have any M here, meaning no moment. It can do slide in this direction, and the only thing that this thing cannot do is going left and right, and that's why you would have only one single force here named AX. Right now I have 3 unknowns, 3 equations, and I can solve this. At the next video I would try to show you how to deal with the 3D problems using the same idea and the same concepts. Thank you.